Hello and welcome to my talk on mobile manipulation leveraging multiple views. My name is David Watkins and let's get started. Shown here is a robot navigating through an environment. The robot is navigating towards a target object that it means to pick up. And what it's going to do when it arrives at the target object is it's going to segment it from the environment. And by doing so, it will create an initial completion using only a single view, and then it will determine what a next best view is only using voxels on the decision boundary. To navigate to this next best view, it will reconstruct its nearby environment and create an image of what it will see at the goal location that is considered the next best view. It will then navigate around to that next best view, reconstruct the object using both the first and second view of the object, and then it will plan a grasp that it will then execute on the object, lifting it up from the pedestal. Mobile manipulation is a very challenging problem. It relies on heuristic or rule-based strategies, but we can leverage big data, deep learning, and simulation novel technologies to improve reconstruction quality and mobile manipulation. This method is best in terms of success weighted by path length and the reconstruction quality of the objects in front of the mobile robot. This method is able to capture multiple views without registering the views together. It uses a novel next best view method, and we can use mobile manipulation without localizing the robot at runtime. Let's go over the pipeline. This robot takes in an image of a goal object and a panoramic target goal. It then navigates to the target object via the panoramic target goal. We then isolate the object's geometry from the environment, and then we perform an initial reconstruction and plan a next best view on that object. We then reconstruct the nearby environment and navigate to the next best view using this novel nearby reconstruction. We then perform a two-view reconstruction using the two disparate views kept in their own image frames, and then finally we manipulate the object by lifting it. Let's first start by talking about how we implemented the RGBD navigation system without localizing the robot at runtime. The agent starts off with a panoramic target goal, the four previous images as well as the current view. These are all passed into an autoencoder to reduce the size of the embedding of each image. These autoencoded images are first passed into a goal checker module that assesses whether or not we're at the goal location between 0 and 1. If the goal checker reports 1, we spin in a circle to assess that we are done. Otherwise, we use a policy model that outputs forward, left, and right commands. This uses the history buffer, the current view, and the panoramic target goal to output a command that updates the environment that the robot finds itself in, and thus we have a cycle that can successfully navigate to a target location in the House 1 environment in the Matterport 3D dataset. Now that we've talked about navigation, let's talk about how we do next best view planning. We can leverage the uncertainty in the reconstruction of an object by determining if there is uncertainty in the reconstruction of it. And by using this, we can calculate the next best view. We do this by first getting a partial point cloud of the object segmented from the environment. We then pass it into a single view reconstruction network to get an initial hypothesis, and then we select voxels close to the decision boundary. And finally, we use principal component analysis for the next best view. For the single view reconstruction, we use an architecture from Varley et al. That uses a 40 cubed partial that reconstructs it into a 40 cubed occupancy grid. We take voxels that are close to the decision boundary of 0.5 plus or minus 0.025, and we compute principal component analysis on these remaining voxels to find the smallest component, which is the optimal next best view as long as it is the farthest distance from the rendered view. The next best view implementation is that the view is extrapolated to an XY coordinate relative to the current position of the robot, and this allows us to navigate to a next best view without localizing the agent. And then we capture an angle that the robot head should be adjusted to align it with the vector that is the next best view, and this angle is used later when the agent has arrived at the next best view location. Now let's talk about how we actually navigate to that next best view location. Remember, we want to be able to navigate without localizing the robot. And so what we do is we plan a nearby view to navigate to based on that next best view. And we capture the nearby environment by spinning the robot in a circle to predict the panorama at the target location. And then we use the learned navigation system described earlier to navigate to that predicted position. This is an example environment that the robot might find itself in. And this is a reconstruction of its nearby environment that is able to be rendered in simulation later for the ground truth panoramic goal. And we can see here that the ground truth versus the predicted navigation goal are almost identical. We then navigate the robot again to get to the next best view location. But once we're there, we need a way to reconstruct the object using two views. And so here, we designed a novel two-view reconstruction architecture that is able to leverage information from previous views in the current reconstruction. And so we can see here that the picture in its single-view reconstruction is missing a handle, whereas in the two-view reconstruction, it was able to leverage the information from the previous view. Initially, we started off with the same Varley et al. Architecture that used a dense reconstruction at the end. We expanded it by adding a deconvolutional decoder, and then we expanded it further by adding a second head to the network that's able to leverage the previous information by adding the two embeddings together to produce a decoded reconstruction. To train this model, we used two datasets, YCB and the GRASP datasets, and we additionally used a challenge dataset of objects from ShapeNet that were not observed during training. And we can see in these examples that the two-view reconstruction is able to correctly identify how far back an object should extend, whereas the single-view reconstruction is not able to use that information effectively enough. We performed a series of ablations on different model architectures that are all described in the paper linked at the end of the presentation. And we found that our two-view split conv proposed model performed best in terms of qualitatively and quantitatively. We also performed an ablation comparing the next best view versus capturing an opposite view, and found in many cases that the opposite view either confused the network, which was trained on random views, or was unable to capture specific geometry of the object, such as when it missed the handle in the picture, shown here. We use three different evaluation metrics: the Jacquard quality metric, or mean intersection over union, the Hausdorff distance, and a simulated Barrett hand in GraspIt, where we calculated the intended grasp using the reconstructed object and then evaluated the grasp joint error on the ground truth object. And in the ablation study results, we found that our proposed model performs best in terms of all three of these metrics. Finally, we manipulate the object and pick it up. To evaluate the performance of our model, we evaluated how the model performed on holdout objects from the YCB and GRASP datasets, and additionally how it would perform on our holdout test dataset from the ShapeNet dataset. And we found that in both cases, our model performed best. Additionally, we compared how our navigation system performs on predicted panoramas, and we found that our model performs well enough that it's able to successfully navigate to the target location, even though it's not able to access the ground truth panorama at runtime. Additionally, we created a new metric, the end-to-end Spl metric, to measure end-to-end performance of mobile manipulation systems. And in using that metric, we were able to evaluate that our predicted model performs favorably when compared against a noisy ROS implementation that had access to the map at runtime. In addition, it performs similarly to the true panorama being given to the agent at runtime in both E2E SPL and GRASP success of lifting the object. Thank you so much for listening to my talk. If you have any questions, feel free to reach out to me or look at the paper at the following link.